Hi, my name is Andrew Kwong, and today I'll be talking about our paper called RAM Bleed, Reading Bits in Memory Without Accessing Them. A computer's main memory is a highly shared resource. Here we have a memory stick, and on a typical machine, this stick might be shared across an OpenSSH server, an unprivileged user, the Linux kernel, a web browser, and even a hypervisor. Note that all of these processes all share the same physical memory module. Why don't we take a closer look at how exactly that might be shared? Here we have memory, which is arranged as a 2D grid where each circle is a cell that contains a single bit. On a typical machine, a browser's memory might occupy all of row 3, an SSH server's memory might occupy half of row 1 and half of row 2, while an unprivileged user's memory could be interleaved between the others. With this setup, notice that cells from different security domains are located right next to each other. Now normally, this should be okay, because any attempt the unprivileged user makes to access memory that does not belong to him is blocked by a combination of software and hardware, which enforces isolation between the processes. With RAMBleed, however, we challenge this assumption and ask the question, does the close proximity of cells somehow lead to data leaking across these boundaries, thereby allowing an attacker to directly dump memory across security domains? As you may have heard from the news, the answer is yes. We can dump memory, and to demonstrate the implications, we developed an end-to-end attack for reading out a 2048-bit RSA key from OpenSSH. Before I begin to describe the specifics of how RAMBleed works, we first require some rudimentary background on how DRAM works. I'll illustrate with an example. Here, DRAM is again a 2D grid of rows and columns, and the CPU requests to read some data that is located in row 3. In order to read data of any size from a given row, the entire row must be activated, not just the data that was requested. And so this data request activates all of row 3 and moves the entire row into a structure called the row buffer. Finally, the requested data is forwarded to the CPU. Then, if the CPU wants to read a piece of data located in row 1, all of row 1 is activated before it replaces row 3 in the row buffer. Finally, like before, the requested data is served to the CPU. Now that we have a cursory understanding of how memory works, we can talk about rowhammer. First, we need to understand the rowhammer effect and how to use it to write to another process's memory. It has been observed in prior research that if an attacker repeatedly triggers activations of rows 1 and 3 in rapid succession, it can induce bit flips in row 2 due to parasitic current draining charge from the capacitor storing the value in row 2. This is called the rowhammer effect, and note that the bit flip occurs across security domains. This means that if an attacker has memory on rows 3 and 1, he can write to memory in row 2, which potentially belongs to another process. When the corrupted data is requested from memory, the error percolates upward and is visible to software, thereby compromising memory integrity. With RAMBleed, however, we want to show that beyond writing, we can also use rowhammer to directly read from other processes' memory. This relies on a more subtle property of rowhammer, and that is that rowhammer-induced bit flips are data dependent. To illustrate with an example, here we have a striped pattern, where the bits in a column are 0, 1, 0. In this case, when we hammer rows 3 and 1, the bit in row 2 is more likely to flip to a 0 due to the opposite charges of the surrounding bits. Now, if we have a uniform pattern of 1, 1, 1 in a column, then the bit is less likely to flip even after hammering. Striped patterns result in flips, while uniform patterns do not. Thus, if an attacker can somehow induce frequent activations of rows 3 and 1, then by observing whether or not a bit flips in row 2, he can infer the likely values in rows 1 and 3. In this manner, the data from the outer rows bleeds into the middle row. Now, at this point, we have described the RAMBleed effect, but it's still not clear how this can be useful to an attacker. In order to take advantage of this effect to read something useful, there are a number of challenges we must first overcome, and I'll demonstrate how we overcame each by walking us through a concrete example, one in which an unprivileged user process extracts an RSA key from an OpenSSH server. The first challenge is for the attacker to acquire the memory layout shown here. Here we have 3 rows on a DIMM, and each column is a 4K page. The attacker wants to locate and acquire the memory in blue, which occupies 3 consecutive rows within a single bank on the DIMM. Remember, however, that the attacker is an unprivileged user process and operating on a virtual address space, but needs to acquire memory that is arranged this way geometrically on the DIMM. To accomplish this, we developed an attack on the Linux memory allocator, which I will now describe briefly. In the red box, we have the virtual address space that the unprivileged attacker is operating on. These addresses are translated into physical addresses, represented by the green box. Finally, the memory controller must map the physical addresses to locations on the DIMM. We will work backwards, from right to left, to figure out how the attacker can overcome each step. Previous work by Drama reverse engineered the mapping from physical addresses to locations on the DIMM, and for our setup, the low 22 bits are used for bank addressing, while the row index is determined by bits 18 and above. What this means for us is that if the attacker can somehow obtain the low 22 bits of the physical addresses, he knows the relevant bits used for DRAM addressing and can map physical addresses to locations on the DIMM. We found that if we could obtain 2 megabytes of physically sequential memory, we could combine Drama's row buffer timing side channel with their mapping function to learn the low 22 bits, thereby enabling the attacker to map addresses to the desired locations on the DIMM. To obtain the physically sequential 2 megabyte block of memory from an unprivileged process, we repeatedly made allocations to exhaust the Linux Buddy allocator, until finally, future allocations were forced to be carved out of the largest blocks that are tracked, thereby giving the attacker 2 megabytes of memory that is both virtually and physically sequential. Monitoring the state of the memory allocator was made possible by the page type info file, which provides detailed information on how many memory blocks are available of each size. And while the file now requires super user privileges to read, it was world readable at the time of publication. I've described the major components of our memory massaging technique here, but the precise technical details can be found in the paper. By combining these steps, the attacker can obtain and identify virtual addresses mapping to the desired locations on the DIMM. After having obtained the memory with the desired geometric configuration, the attacker next needs to find a way to place the OpenSSH server's keys in target page 0 and target page 1. To overcome this hurdle, we developed a technique, which we call frame feng shui, that enables the attacker to place the SSH server's RSA key in a frame of the attacker's choosing. In exploit terminology, feng shui is a technique for manipulating some structure into an exploitable state. In the case of frame feng shui, we are manipulating the page frame cache such that subsequent memory allocations are placed in an attacker-chosen frame. Let's walk through an example of how frame feng shui works in action, with an example victim that executes the pseudocode shown. The victim is going to request 4K pages for both buffer 0 and buffer 1, before finally requesting another page to place a secret in. For this example, we will assume that the attacker starts with the frames from the previous configuration, along with 2 other frames, X and Y, for a total of 7. One of these is mapped to target page 0, which is where he aims to place the victim's data. If the attacker first deallocates T0, this frame is claimed by the page frame cache. The page frame cache acts as a buffer that attempts to serve memory allocation requests before they reach the buddy allocator. It operates in a stack-like manner. When a frame is deallocated, that frame is pushed onto the page frame cache, while allocations are popped from the page frame cache. Thus, the deallocation of T0 pushes it onto the page frame cache. Since the victim makes 2 allocations before the secret, the attacker then deallocates X followed by Y, which are pushed on top of T0. Then, if the victim executes the first line of code and requests a new page, Y will be popped for the victim to store buffer 0. The second line of code's request will be served by X. Finally, in the last line of code, when the victim requests memory to place its secret in, target page 0 will be popped and served to the victim, as intended by the attacker who placed it there. The final result is that the victim's secret is located in the attacker-chosen frame, which is mapped back to target page 0. An attacker can abuse this frame feng shui technique to land the SSH server's RSA key in the attacker's chosen frame by first performing its deallocations, and then synchronizing with the victim by making a TCP connection to the SSH server. This triggers the SSH server to load its signing key into memory, so that it can authenticate itself. And when the SSH daemon requests a 4K allocation to place its RSA signing key, the page frame cache will pop the chosen frame, target page 0. And so now the secret is placed where the attacker wants it. We also want to place a copy of that same secret below the sampling page. In order to do that, we can make another TCP connection in parallel with the first, resulting in 2 copies of the key in memory. As long as we do not terminate either connection to the SSH server, both copies of the signing key remain in memory. And finally, we have obtained this exploitable memory layout, where the blue pages belong to the attacker, and the red pages contain the secret. To begin reading bits from the secret, we first start with a flippable bit in the sampling page, and we'll set it to 1 before trying to read the secret bit above and below. For this example, we'll assume that the corresponding bit in the secret is 0, which results in a 010 stripe pattern. This means that if we can somehow induce rapid activations of the secret pages, Rowhammer should cause the bit in the middle to flip to 0. The outcome of whether the bit actually flips reveals the corresponding secret bit. In this example, because the middle bit flipped to 0, that means it was originally in the middle of a 010 striped configuration, which reveals the secret bit to be 0. Otherwise, the secret bit was a 1. Now, how does the attacker actually force activations of the secret pages if he does not have any permissions to read or write to them? Recall that when DRAM is accessed, the entire row that contains the requested data is activated. This means that if the attacker accesses his own memory in A0, A2, the attacker also activates the cells containing the secret, which are then used to induce bit flips in the sampling page. We have now read a single bit. To read the next bit, we need to first search through memory and locate a page with a bit flip at the desired offset within its frame. Once we locate this new set of frames, we repeat frame feng shui, set the flippable bit to 1, hammer the activation pages, and read another bit. Here, the bit in the sampling page does not flip, which reveals the corresponding sacred bit to be 1. We can repeat in this manner for all the desired bits. We chain together the techniques described thus far to develop an end-to-end attack wherein an unprivileged user process extracts a 2048-bit RSA key from an OpenSSH server. We were able to recover 68% of the bits from the RSA key at a rate of 0.31 bits per second with 82% accuracy. The problem with this is that of the recovered bits, about 250 of them are still incorrect, and we don't know which subset of the bits are incorrect. To overcome this, we turn to the Hender-Shaham algorithm, which, given about 27% of the bits at random, can exploit the redundancy present in RSA keys to recover the entire key. Since we don't have 100% accuracy, though, on our recovered bits, we used a variant that handles probabilistic partial key recovery, which is why we needed to read out 68% of the bits. Using this algorithm, we were able to read out enough bits to fully recover the key in a couple of hours. So now we have demonstrated RAM bleed against desktop machines, but what about server machines? This is complicated by the fact that server machines employ error-correcting code memory. ECC memory aims to correct corrupted data words when they are read back from the DIMM, which directly counters the Rowhammer effect. Let's see an example of how this works. If we hammer rows 3 and 1, the bit does in fact flip on the DIMM. When it is read back from memory, however, the ECC mechanism corrects the error and writes the correct value back to the DIMM. Thus, the error should be invisible to software. This is not actually the case, however, as ECC Plate from SP19 made the observation that data words with errors have a much longer read latency. This is due to the synchronous nature of the ECC mechanism, where multiple levels of software must execute before the value for the read is returned. Here you can see latency spikes 5 orders of magnitude larger than average. This means that an unprivileged user process can easily detect when a bit has flipped by simply timing read latencies. And what does this mean for RAM bleed? Recall that RAM bleed only requires the attacker to detect whether a bit flipped or not, and doesn't require the bit flip to be persistent. Thus, the timing side channel enables RAM bleed on ECC memory. Let's see how this works with an example. Assume we have the same memory layout as before, with a flippable bit set to 1. If the bit lies in the middle of a stripe configuration, then after hammering, the middle bit flips to 0. When the attacker reads the victim bit, however, the ECC mechanism corrects it so that the attacker always reads a 1. This correction process, however, results in a large read latency, so when the attacker times this access, he determines that the bit flipped. This means that it was originally in a 010 stripe pattern, so the secret bit is revealed to be 0. Therefore, ECC memory does slow the attack, but does not prevent RAM bleed. In conclusion, we have shown how Rowhammer is not restricted to integrity, but have extended it to directly breach confidentiality as well. To demonstrate the implications, we developed an end-to-end attack against OpenSSH that allows an unprivileged attacker to fully extract a 2048-bit RSA key. To accomplish this, we also had to develop new Rowhammer attack primitives, such as an attack on the Linux memory allocator for mapping virtual addresses to DIM locations, all from an unprivileged user, and our frame feng shui technique for maneuvering frames into a frame of the attacker's choosing. Finally, we also showed that ECC in memory does not stop Rambleed, even when all bit flips are corrected. Thank you. I'm happy to take questions now, and my contact info can be found at this URL.